So, hello and welcome everyone. I'm joined today by Tony Giampaolo, the author of the forthcoming second edition of the book Compressor Handbook Principles and Practice. Hi, Tony, and welcome.
Hello, Anna.
So, for starters, can you please introduce the book to us and tell us who is it for?
Yes, I wrote this book primarily for young engineers, but plant operators and plant maintenance personnel to understand, have a better understanding of compressors and the different types of compressors. So uh, I go over quite a bit in the first edition on compressors. This second edition addresses primarily seals.
So some chapters have been added in this new edition, chapter on seals. How important are seals to the function of compressors, and why add this chapter now?
Seals, seals have always been important, but seals have been improved over the years. Uh, Without seals, we could not accomplish the compressor ratios that we need for a lot of applications. Without seals, we would expand a whole lot more horsepower. So by having seals and having the proper seal in the compressor and in the right place, really not only enables us to accomplish more with the compressor, but also do it at less horsepower expense, also less cost, because the more horsepower you need, the more it's going to cost. Seals are also extremely important in protecting the environment from the types of leakage that you can have in a seal or in a compressor, depending on the type of uh, gases that are being compressed.
And throughout your writing process, were there any particularly challenging or intricate details, concepts related to compressors that you found interesting to explore and explain in detail? So,
Uh,
how did you approach breaking down these complex ideas for your readers?
there were some things that really involved primarily error problems. Uh, there's some problems that are developed during the design process that materialize when the compressors get into full service. Other problems develop later on in the compressor operation. Sometimes the material being compressed is not as clean and pure as you would hope. It might have contaminants in it. Uh, Simple example, I've seen compressors that have failed uh, day one during the initial application because during the assembly of the compressor and installation, sand was allowed to get into the piping. And when the process gas was introduced, that sand was pushed through the piping into the compressor itself. So seals that deteriorated rapidly, or in some cases never even properly sealed. So these are problems that can be avoided if people have a good understanding of what they're doing when they assemble a compressor and when they operate a compressor. Uh, Once the compressor is in place and properly installed, it can operate fine for as little as a week or two, and then the problems start to materialize. Or it could take several years for the problem to develop. Knowing what to look for and how to look for it is the basis of what I hope to put into the book. I wanted the reader to understand the thought process of identifying problems because problems are not always obvious firsthand. Sometimes the problems are not obvious at all because the instrumentation that's used is inadequate. In other cases, the process is picked up fairly quickly, and when that happens, the operator will have a better understanding of what to do to repair it.
Hmm. And building up on that, can you share some of the case studies included in your book that illustrate the principles you've covered, and how did these real-world examples help readers better understand and apply the concepts discussed?
Yeah, the case studies in the book, actually the first case study was not as much a problem solving, but a control technique application. The first case study deals with operating both positive displacement and dynamic compressors in the same environment. And they came about because I had a client that had a centrifugal compressor compressing gas for his gas turbine operated power plant. He wanted to add another compressor, and put in another centrifugal compressor would have been very time consuming and expensive. So he wanted to put in a positive displacement compressor, but he didn't know how to operate it. Positive displacement compressors have a lot of high pulsations, which are not good for a gas turbine. To have fuel coming in pulses tends to make the gas turbine operate unstable. So I came in and developed a control process that operated the positive displacement compressor at a final throughput very similar to the centrifugal. So the control system really allowed the operator to start on either one of these compressors, switch over at any time that the compressor needed to be, primary compressor needed to be shut down, and the secondary compressor needed to be brought online. And I wrote the program so that either compressor could be primary or either compressor could be secondary. And the operator could then stop, repair the secondary compressor, whichever one it would be in that particular case. Was faced a lot of resistance from a lot of the people in the plant, but when it was finally completed, they embraced it wholeheartedly. In fact, about a year later, I used the same application in another plant in another process where they had two centrifugal compressors driven by gas turbines and one recip compressor driven by an electric motor to provide throughput to the downstream process without any pulsations. So that was one of the case studies. It's the first one in the book. Other case studies dealt with piston rod runout. In a recip compressor, the piston rod's moving back and forth. Usually it's horizontal, but in some applications it's vertical. And the runout can be such that the piston will either cause a lot of friction on one side or it actually could wobble. So that one went through the process of determining piston rod runout. Another case study had to do with pulsation bottle design. The whole process of pulsation bottles is to even out the gas flow, to take the pressure blips out of the system. So that went through that kind of detail. A third case study had to do with valve problems. As I mentioned in the first started talking about the problems you can have with reciprocating compressors, is valves can be a problem. They can either not seal properly, or they could float, or the valves could be could deteriorate rapidly because of contaminants in the gas. So that third, fourth study dealt with pulsation bottles. I did not put in a case study on anti-surge. That was in the first edition. I thought it was addressed quite sufficiently. Surge is a problem with centrifugal compressors. It's something that's not really easily understood. In many cases, it's not even recognized when there is a problem like that.
Right. So the book mentions the use of different types of instrumentation for compressor control. You mentioned now valves. Could you provide insights into the selection process for these instruments and highlight which ones are most effective in controlling surge?
Yeah. In many cases, if the operator wants to just measure throughput of the system, he wants a very reliable control measuring flow. And generally, they'll use a digital control system that will sample the flow signal. But after about every 250 milliseconds, that sample is averaged, and that's the information that's sent to the control system, and that's fine for throughput control. It's slow, but it's not super slow, but it's not. It doesn't involve a lot of quick response that's needed for the flow system. Move into something like anti-surge and instrument that's not giving you information but every 250 milliseconds is much too slow because surge can occur in 50 milliseconds. So you can have 5 surge cycles before the sensor even recognizes it and sends it information to the controller. So in that case, we'd want to have instrumentation that will respond in 5 milliseconds. And that's primarily, we find with the digital instrumentation, we can accomplish this. So we can take a 5 millisecond signal and we can average it over 250 milliseconds if we're doing it for, say, throughput control as we would in the sales gas application. But if we want to control something that's actually very quick responding like surge, we can have a signal that's updates every 5 milliseconds. This goes along very nicely with the control systems, uh, computer controls that will run through the entire control process. Every algorithm in the control system can be reviewed and sent forward in usually 5 to 50 milliseconds. So digital controls are extremely important. They work very well with both the fast anti-surge control system as well as the much slower throughput controls.
Hmm.
So speed of response is important. Accuracy is important for say sales gas numbers, but accuracy is not super important if we're looking at anti-surge. What we're looking in those cases is a control system that's repeatable and an instrument that's repeatable. So the better an instrument repeats, the more accurate the data is, the more obviously we can recognize surge as soon as it starts and not after it's went through 5 or 10 or 15 cycles.
Hmm. So I was saying, as technology and industry practices evolve, you've mentioned, for example, digital controls. What emerging trends or advancements in compressor technology do you think will have a notable impact on the content of future editions?
Uh, right now, I think the design of pistons, the design of impellers, has reached a level where any improvement is going to be very, very minor. But the improvement in control systems, I think, still continue to be uh, probably the biggest contributor to improving the operation of compressors. Uh, we have the ability now to demonstrate on a computer screen where the operating point is relative to where surge is, relative to where the target throughput is, say target gas throughput. Uh, those that ability gives the operator the ability to see actually what's going on in the compressor. This technique probably is only about 5 to 10 years old. Before that, the operator really had very little understanding or feel for what was happening. And back in that time, operators would primarily address the signal as, say, I'm having a problem with the compressor making noise, not knowing what the noise meant or what the damaging effect were of the noise. In some cases, it's liquids in the compressor. Other cases, it's surge as a compressor. So any one of these things can be much more easily depicted on a computer screen, which helps the operators to understand what's happening. And the control systems are now to the degree that they will actually shut a machine down when it sees that there's a problem within the machine.
And there is an ever-growing drive towards more sustainable energy practices. How do compressors play into this?
Uh, that's a more difficult one. The compressors that have reached the state of the art contribute by the fact that one, they're not leaking any of the processed gases to the atmosphere. One of the big problems over the years is a compressor that was compressing, say, methane uh, gas, or say boosting pressure to a gas turbine engine, methane leaking to the atmosphere. We find that this is objectionable. We don't want that methane out there. It does affect uh, what, what we see in the environment, in a very close environment where a compressor is providing fuel gas to a gas turbine in an enclosed building, and that can actually contribute to too much methane, free methane, which could end up in an explosion. There was a case that I was involved in many years ago where a gas compressor was leaking so much methane into the surrounding area that the methane, when it finally reached a level, reached a level of the air that contacted the hot surface of a gas turbine, it ignited and there was a flash fire. Uh,
Mm-hmm.
and in that case, there were two individuals that were burned, not critically. I mean, no one passed away. Fortunately, for one of the operators who was in that area, he was wearing a full personal protection
Mm-hmm.
coverall, which really the only things that burned were the back of his neck and a little bit on the back of his hand. He was facing away from the flash. However, his coworker had on a shirt that was not made of cotton. It was a short sleeve. It actually melted on his back. The fire burnt the back of his hands. He
Mm-hmm.
was out of work for quite a while until that healed. Uh, so if we can put a compressor out that's going to minimize or eliminate completely leaks like that, and we're really protecting the environment. Uh,
And safety for the people working.
Absolutely, yeah,
Mm.
yes. Uh, we know when we go into a design where we're compressing gases that are dangerous, uh, seals themselves, they're not perfect. It's hard to really get a perfect seal, but we've developed techniques where we can use a intermediate gas, such as a nitrogen, and inject it into the compressor between the two levels of gas pressure, say methane gas, to prevent that gas from leaking out to the atmosphere. Or we can have a collection process where we can take that gas that is leaking to the atmosphere, redirect it to an area where it cannot cause damage. We can pipe it to an overhead pipe system that would release the gas high over your head, so it's not in the environment where someone is working. So these are techniques that are used to control the protection of the machine, protection of the environment around the machine, and the people around the machine.
Okay. Well, we are shortly running out of time, but maybe last question. What would you like the readers to take away from the book?
Well, I'm hoping that the people that read the book will have such an understanding of the compressor that, one, they'll recognize the problems immediately. Two, if they recognize the problem and have took away a lot of the information that's in the book, they will know how to correct the problem. But if they don't, they at least will know that there's a problem that needs to be corrected, and they'll contact someone else, like the manufacturer, either of the compressor or the seals, and they say, "Hey, I've got this problem. I know where the problem is. I don't know how to fix it." And enlist the help of people that manufacture these things or develop better processes, can assist them in getting these compressors under better control. So it's hopeful that they can do this with what they read in the book.
Yeah. Okay. Great. I think this is a great place to stop. Thank you so much again, Tony, for joining me and talking about your upcoming books. So again, Compressor Handbook, Principles and Practice, second edition. I will link to it down below. Thank you, Tony, so much.
Thank you very much. You have a good day.